So we are live now. Hello, everybody. Welcome to the second talk in the series of talks surrounding like the robust speech challenge. The second talk it will be given by Jeremy and Ray, who work as machine learning engineers at Kensho-Technologies. They worked on the Ctc Decode library, which is now integrated into the Transformers library and enables you to improve like the automatic speech recognition. And to tell you more about it, I give the word to you.
All right. Thanks for asking us to do this talk. I'm Jeremy Lopez, and as you said, today we're going to be talking to you about Pyctcc Decode and some stuff about speech-to-text decoding. A bit about us. So we're both ML engineers at Kensho, and Kensho is an AI company that was founded in 2013 and then acquired by the financial company S&P Global in 2018. And since then, we've been powering a lot of S&P's AI and tech advancements. And also we've gotten access to S&P's huge amounts of data that we could then use to power the different things that we work on. One of the products that we offer is called Kensho Scribe, which is a speech-to-text solution that produces transcripts from audio. And so the way this talk is going to work is I'm going to give you a brief introduction to Ctc Decoding, and then Ray is going to give you a walkthrough and some examples of the Pyctcc Decode package. And we gave a longer version of this talk a couple days ago for the Hugging Face audio ML study group. So if you want to know more, there's also that video available, which is about twice as long as this talk. So for the first part, I'm going to talk to you about first an overview of a generic speech-to-text pipeline that you're likely to see, and then a review of Ctc encoding and speech-to-text, and then talk about a little bit about how to decode Ctc encoded output. So first of all, a review of a standard kind of architecture. So obviously for speech-to-text, you want to start with an audio sample. So like an MP3 or a WAV file. And probably the first thing you want to do is to perform some sort of pre-processing to get features for every chunk of audio that's some number of milliseconds long. And once you have these features, you typically will pass the generated per timestep features into some sort of neural net model like Wave2Vec or CitriNet, which gives you back some per timestep logit matrix. And this logit matrix typically will then give you softmax logits predicting character probabilities for each slice in time through your audio. And often these characters are going to be actual characters like Latin letters, but they could be something else. But typically it's roughly predicting regular characters. But these are character probabilities that have a twist there. So as I said, the audio is typically sliced into evenly spaced chunks of time, and you'll predict these logits for each slice. And this means that any kind of output length you get from this is going to be proportional to your audio length and not your text length, which is a complication that is the reason why you have to go to Ctc encoding, which I'll talk about in a bit. But once you get these generated per timestep logits, typically what you want then is that you need to have some sort of decoder that takes this matrix and returns some sort of hopefully human readable text. And so this is what we're going to be talking about today, which is roughly how this works. So I'll give you a review of Ctc encoding if you haven't seen it before. So this stands for connectionist temporal classification. And the reason why you need to have some sort of encoding is there are some challenges in decoding these logits. So typically you'll have many more time steps than predicted characters. The reason for this is that you need to make sure you have enough slices in time that you could actually have your output be long enough, regardless of how fast someone is speaking or the kinds of words they're saying. But also we have things like duplicated characters in actual words, like in the English word hello, there's 2 L's. And the reason why that's important is that when you actually get the output of this whole process, you need some way of collapsing repeated characters without also eliminating duplicates. So for example, if you have these two outputs, both of these clearly represent the English word hello. And so when you decode this kind of string, they should both decode to the same exact thing. And the reason why you can get this is that, if someone speaks at fairly fast, maybe you just automatically get out the word as your output. But if someone speaks much slower, potentially you'll have several copies of each letter in your output. And so when you decode this, this is still the English word hello, just said much slower. So you have several slices for each actual character. And so what you can do here is you could add a new character to the alphabet that represents a break between characters. Often it's going to be denoted like something like pad or just an underscore. And so when you have these repeated characters, you can try to have your model insert this break character in between the L's. And then you can decode these with a two-step process of first removing any duplicate characters and then removing this extra Ctc break character. And that will take these two strings and produce, in the end, the English word hello for both of them. And so this is what you do once you have a string you want to decode. But like I said, what happens is that the audio models you'll often be using will output this logic matrix. And so you have to then now take a logic matrix and produce a string, a Ctc encoded string that can then be decoded. So we need to decode this Ctc encoded output. So there is an easy way to do this, a very simple way that you could probably code up in just a few lines, which is to do a greedy decoding that takes the argmax of each time step. So you go through your logic matrix, and at each time step, you just take the most likely character. And then from that string, you can then run this two-step process of removing the repeated characters and then removing the Ctc character break character. And that gives you a way to go from this matrix to a string. And this potentially is often decent, but it's probably not optimal. There's a number of issues that you can run into. So like in English, homophones are fairly common. So you can run into something like the noun not versus the word not meaning negation. Both of these are pronounced the same way. So a model might actually confuse them. There's also just misspellings that can happen. And many kinds of small errors. So, for example, in English, F and PH and GH and so on can all give you the exact same sound. So you can then ask yourself, well, what happens if I run the word for through my model and it wants to output the text PHOR? That would be pronounced for, but it's not an actual word. So if you're an engineer, like an ML engineer and a data scientist, you might want to think, well, what if I then, to correct this, I just collect a lot more data, I retrain all my models and see if that fixes it. And so that sounds reasonable, but there's a number of issues there as well, where that can be very expensive and that can be very, very time consuming to actually collect data, to retrain models. And even then, in the end, you might actually find out you haven't actually fixed these kinds of issues. So that you actually might need to rethink how you're doing things a bit. So we can consider two different things. So first, can we inject more information about language to try to guide the decoding process to give you more natural sounding language? And second, can you use a better decoding strategy? So I don't want to go into details, but we go into more of this in the longer version of the talk. But you can use beam search instead of this greedy decoding to consider multiple possible decodings. So you can build up different outputs and try to consider several of the higher weighted ones to try to give you more options to give you better results. But I'm going to go into a bit more detail about language modeling. So ultimately, what you want to do to try to guide the decoding is you want to be able to score how likely a given text is, given that you have this logic matrix that represents what the audio was, but also you probably have a lot of text that gives you some sense of what normal language looks like. And we can use this to try to remove improbable parts of the predicted text. So even if the audio sounds a lot like something that is very unnatural sounding, we can then hopefully remove it or downweight it based on the fact that we know that maybe this is not normal sounding text and there's something that's not quite as highly weighted, but is much better. And so one common way you can do this is with an n-gram language model. And so these are something that they're fairly traditional, and I think it was existed long before deep learning became very popular. But they're probabilistic models where if you given some sequence of size n-1, you can try to predict what the nth word is, or what the probability of the nth word being some particular word. And by doing this, you can try to identify improbable sequences of text that might need to be changed. And so again, this is used in conjunction with logits, so that way you combine both your audio and your sense of what natural language looks like to get you the best possible output. So for the purposes here, a language model is basically just something that you take some proposed text, you put it through your model, and you get some score likelihood out. So for example, if you have the English text, the angry brown cat, that sounds pretty much like natural English. So probably you want to have a decently high score. So maybe your language model assigns some probability or likelihood of, say, 0.4 something for that. But if you have the text, the angry cat brown, that's much less natural sounding in English. So that probably gives you a much smaller result. It's probably not 0, since there could be cases where that text could appear in actual English, but it was just not as common as the previous text. So you'll give it a smaller probability. So for a more concrete example, you could have a bigram language model. So this is an n=2 language model. And so if you throw in some text like the first line from A Tale of Two Cities, what the probability of this text would be is just the combination of the probabilities of each word given that what the previous word was. So in bigrams, you only include the single word prior to each word. And so then the bigram model just needs to then memorize probabilities for these pairs of words. And you can go to higher and higher ends. You can go to n=3 or 4, but you can't go that much higher than probably n=4 or 5, just because at some point you just don't have enough samples of a word with 5 or 6 previous words before it, so you just can't get good probabilities for those. And so the way you could potentially incorporate this is that as you're decoding a piece of text, you can then build it up, like in beam search. You iteratively build up your text, and at each point you could ask yourself, well, what is the probability of this text given the logits? So what does the audio say? And then add in, what does the language model say? And the idea here is that if you have very strongly disfavored text, you could have a large penalty that goes into your score for this text. And if you have very natural sounding text, you have a much smaller penalty. And by doing this, you could then guide yourself to try to choose mostly things that sound the most like natural language. And so that's all I want to talk about for this first part. Like I said, if you want to know more, there's a longer version of this talk. But just in conclusion, Ctc Encode is a pretty common way for audio models you're likely to see to output character information. And then the Pyctcdecode package that you hear about next decodes Ctc encoded logits using beam search, and also allowing for you to add a language model to help assist your decoding to give you more natural sounding output. And now from here, I'll let Ray give you more information about the Pyctcdecode package.
Awesome. Thank you, Jeremy. So on to Pyctcdecode. First of all, I've included a few links here to places you might find more information. Obviously, the first is the actual Pyctcdecode repo. And I've also included a link to the demo code that's used to generate the examples here. And of course, we gave a more detailed version of this talk with more information, and I've included the link there. So Pyctcdecode is a package that we developed at Kensho to decode Ctc encoded logits. It's implemented in Python, which means that it's fairly simple to code and also makes it fairly easy to extend with new features and hopefully easy to use in common ML workflows. Although I don't want to, pat ourselves on the back too much. And everything that Jeremy discussed in part 1 is implemented. We use beam search to determine the quasi-optimal output text. We offer language model support with KNLM as our package for language models on the back end. And of course, you can do greedy decoding if you just don't include a language model and use a beam width of 1. And we also offer some additional features. So the first thing that we offer is Hotword Boosting. Basically, you can add hot words as a list and then boost the probabilities in the n-gram language model of each hot word appearing. This is extremely useful when speech conditions might be different from those that your model was trained in. An example of this is early in 2020 when COVID and coronavirus became extremely common in the English dialect, but there weren't a lot of training samples that actually contain these words. And Hotwords is implemented pretty straightforwardly. We just take the probability that Jeremy talked about in the first part, and in addition to the probability from the logits and the probability of the text from the language model, we add some flat bonus if the latest word is a hot word. We also offer comparable speed to all of the other decoding packages that I've previously used. And we achieve this despite being coded in Python by aggressive caching and extensive use of beam pruning. So we reject any beams that achieve a particularly low probability at any point. And we also cache partial results during calculation, so we don't need to continue calling the language model for very similar strings. I don't know if I can actually say the package we were using previously. I don't want to throw any shade, but you can see here that we achieve a actually faster runtime than the package, while also maintaining and even beating our previous WRs. And of course, there's lots more that we want to do with this package. If you have any suggestions or would like to see any features, feel free to submit a feature request on the GitHub. So let's get started with actually implementing Pyctcdecode. It is a Python package, so pip install seems like a good place to start. But jokes aside, to start using Pyctcdecode effectively, you really need 4 things. You need a text corpus. Ideally, you'd want the same text corpus that was used to train your acoustic model to train your language model. You need an acoustic model. We handle both byte-pair encoded and character-based acoustic models. And if you're looking to use a pre-trained model here, Hugging Face probably has all of your needs covered. You need to have access to the vocabulary set for the above model. And then, of course, you need KennelM so that you can train your n-gram model on your text corpus. So where would you look for a data set? The data set we used in the demo repo is Speech2Speech. It's 5,000 hours of financial audio and associated transcripts, which is approximately 5 times the size of LibreSpeech. Highly recommend it, although this is a bit of self-promotion. Speech-to-Speech consists of company earnings calls that are split into short chunks to allow for easy training of speech recognition systems. We've got almost 50,000 unique speakers with a variety of accents and speaking conditions. And also the train and val sets are the result of manual transcription, which means that there's very well-normalized text that has very polished orthography. For an acoustic model, again, we can handle both byte-pair encoded or character-based. And the only thing you need here is the vocabulary set that the acoustic model uses. I've included a snippet here using the Hugging Face Wave2Vec base model. This is the model I use for the demo examples that I'll talk about shortly. And then the final thing that you need is a KennelM model. And again, KennelM is a Python model. Instructions for training your model on a text corpus, such as Speech are included in the demo repo. And I can't stress enough that matching vocabulary sets is critical. Even a very slight mismatch in the characters used to train the language model can lead to some very, very strange behavior on the back end. So let's get started. The first thing you need to do is build your actual decoder. It takes the vocab, the KennelM model location, and some params, and then you can decode an actual logic matrix just by calling decode. And let's look at some samples to get a feel for how language models actually work in practice. I tried to pick a spread of examples, including some where the language model is very effective and some where it is not. And hopefully this gives you a good idea of the kinds of errors that language models tend to fix and the kinds of errors that they might introduce, and also how to tune them. Again, all the code is available. So let's start with a sample where the language model performs pretty well. And here's the audio.
I also want to remind everyone that any forward-looking statements made during this call are subject to risks and uncertainties, the most important of which are described in our press release and SEC filings.
So this is a pretty straightforward sample. The audio quality is quite good, and so we would sort of expect any acoustic model to perform fairly well. And indeed, if we look at the greedy decoding for this sample, the language model does perform quite Well, the only two mistakes it makes are at the very end. Instead of press release, it says press relief. And instead of SEC filings, it says SCC filings. So, of course, these are the sorts of errors that we would expect a language model to be able to address extremely adequately, because the phrase press release is very common, especially in financial corpi, as is SCC filings. And indeed, if we pass this through a decoder trained on speech, it fixes both of these errors without an issue. But now let's look at a sample where the language model performs a little bit less well. And here is the audio for that.
Thank you, Ivan. I'm now going to look in a bit more detail at what is, as Ivan said, a good set of results with better top-line performance, margin expansion, and increased cash flow.
So again, this is a fairly clear audio sample, and we would hopefully expect an acoustic model to perform fairly well on this. And if we look at the actual greedy decoding, it does indeed perform fairly well on this. The only mistake it makes is at the end. Instead of cash flow being 2 words, it's agglomerated into a single word. Unfortunately, if we pass this through a language model with default parameters, instead of the initial phrase, "Thank you, Ivan," we get back, "Thank you, even." And this is an unfortunate error, excuse me, because we sort of expect that a language model will return something that's more understandable English, and "thank you, even" is not even correct English. And this is probably because, even is much more common than Ivan is in any n-gram model. But despite these sorts of errors that are introduced, it's worth noting that language models are still very useful. We see a pretty significant improvement in WR on our internal work, and this is even with a very large and highly trained acoustic model, so they can be useful in almost any speech-to-text scenario. Of course, this doesn't change the fact that they still introduce these errors. So how can we address errors that the language model introduces? So we have 2 options with the package. The first is we can use our Hotword feature from before and boost Hotwords for things that may be specific to our prediction domain. So things like names, such as Ivan, for people on a call that we know are on the call. Words like COVID that may be common in current speech, but not in our training corpus. Or we can adjust the parameters to sort of increase and decrease the weight on the language model to try and capture as much of the benefits without introducing as many of these errors. So let's try Hotword Boosting on our previous sample. And Hotword Boosting is very straightforward to implement. Basically, you take a list and you can pass it to your decoder.decode call with some weight. This increases the score by whatever weight you pass it to. And on our previous example, we have the correct ground truth and the correct greedy decoding. And now, if we pass it with the Hotwords, instead of changing the first "thank you, Ivan," it actually fixes it. And in addition to that, it'll improve the WR of the sample because it fixes the error where cash flow is 1 word, properly separating it into 2 words. So this is very useful in many common transcription scenarios, including in a lot of production scenarios where you might need to adjust your model without retraining the whole thing. But sometimes this isn't enough. So let's look at our second method of improving language models, which is parameter tuning. So Pyctcdecode Decode offers 2 main tunable params. There are also, a few others that are possible, but these are the 2 most important. So alpha is basically the weight on the language model versus the logits, and beta is a constant, and it's hard to sort of get an intuition for what adding a constant does, but more or less, in my experience, it makes the model more likely to add or subtract words during training. It's important to note that when doing any tuning like this, that it's really, really easy to leak information. If you tune these parameters on your validation set and then score them on the same validation set, you'll get very inflated WER scores. So if you're setting up a pipeline like this, you need to make sure that you pull some sort of parameter tuning holdout out of your training set, maybe a very small fraction of it, and then the rest of your training set can be passed to your acoustic and your language models for training. And your validation set should be completely separate from these. And also, if you're doing this sort of tuning, it's really important to have a visual check. Sometimes if you weight the language model too highly, even if you get a good WR, you can get samples that are really, really bad when humans look at them, just because the language model will sometimes unilaterally decide that something should be changed. So let's look at a sample for this. Here's the audio.
Whereas then in the industrial cranes and crane components business units.
Let's listen to that one more time.
Whereas then in the industrial cranes and crane components business units.
And this is a much more difficult audio sample than the previous two. This is the correct transcription, but when we pass it to an acoustic model, it has a pretty hard time figuring out what exactly is happening. You can see that it's a little confused at the start. The first phrase is jumbled, and then instead of cranes and crane components, we get grains and crane components. And if we pass it to a language model with sort of standard parameters, well, where it fixes the first error, it doesn't actually identify that industrial grains and grain components is probably not very likely English. I don't know why people would be talking about grain components. But if you increase the weight on the language model and then run it again, it eventually gets to the point where it identifies that grains is not really an industrial or component-based item, and it corrects grains to cranes. And you can actually get it to fix both the first cranes and the second crane if you turn up the language model high enough, but it starts to degrade performance in other areas, so I've left it at this middle ground for the example. Again, I can't stress enough that ensure when you're training these that you don't have any leakage with your validation, or you'll have a bad time. And that's all that we wanted to talk about today. I hope you sort of got a feel for what Pyctcdecode Decode can do, and I hope that you get the opportunity to use it in some of your own speech-to-text adventures. And I think we can pass it back to Leandro for questions or comments.
Thanks a lot for the great talk. I think we have a couple of minutes to answer a few questions. So far, I haven't seen any question in the chat, but feel free to post one if you have any. Maybe in the meantime, since this is like a pretty practical challenge that like the participants of like the robust speech challenge are facing, do you have any like practical tips on how you would approach such a problem? Like if you need to build a speech recognition system for like a rare language, let's say.
Jeremy, do you want to take this?
Yeah, so I think for something like a rare language, I would say this decoding process probably is going to be most effective for certainly alphabetic type languages. So for something that's less alphabetic, so like a language like Chinese, I haven't tried it out, but I would suspect that decoding would be much less effective because you have a character set of thousands of characters and they're not really phonetic. But also I think if it's a language that I mean, this is something that even trying out greedy decoding first to see how, if you have a good audio model, see how it works, and then if you're able to collect a lot of text, just training a language model and throwing that in, it should be fairly easy to do. And yeah, but I think a big thing for language is just whenever you do this, just make sure you're doing some manual checking of things, especially if you're trying to tune parameters, just to make sure there's this embarrassment score that Ray mentioned, which is not really a technical term, but just make sure that you're not making a lot of really bad looking errors that maybe don't get captured in traditional metrics like word error rate. Because I think humans will be very sensitive to pretty subtle language errors.
Awesome, thanks. Still don't see any questions. Maybe we wait a couple of more minutes if any question pops up.
Yeah, I think we're also almost at time. So are there additional events following this one?
That's all the talks for today. There are going to be 2 more talks tomorrow. As far as I know, one from Mozilla and another one from Meta AI about data sets and automatic speech recognition.
Very cool.
So if there are no more questions, I thank you a lot for your nice presentation and wish you a nice evening or nice day.
Thank you.
Thank you.
And thank you for setting all this up. Appreciate it.
There's one question, so maybe we can answer that one. Is it possible to replace your language model with a transform-based one within your library?
Yeah, so this is something that is currently in the pipeline for us. We've been looking at implementing some transformer-based language models ourselves, but it is not yet available in Pyctcdecode. But it is something to look for in the coming months.
Yeah, this is also something that one of the advantages of using Python means that modifications like this are should be very easy to do.
Cool.
Yeah,
That's
I think
exciting.
that transformer-based language models also bring a whole different set of challenges, especially to production systems, just in terms of speed, and it's an additional complex model to maintain. So there are benefits and drawbacks to doing so.
That makes sense. So thanks a lot for your presentation, and enjoy your day. Bye, everybody.
Thank you.
Thank you.